So in our last video, we used the integral test on each of these three examples to determine whether the series converges or diverges. And we found that example 1 and example 3 both diverge because the corresponding integral also diverges. But example 2 converges, right? When we did the improper integral, we found that the integral converges to the value pi over 4. So that means that the series, the corresponding series, also converges by the integral test. It does not, however, converge to the value pi over 4. So let's make sure we understand that. So the next question is, what does it converge to? And the frustrating answer is we're not going to learn how to figure that out. We cannot, using tools that we learn in this class, determine the exact value to which this series converges. However, we can get approximations. Okay, so that's going to be a big part of this whole chapter. Is if we can't get the exact value, at least let's get a decent approximation. So I believe the instructions say if it converges, find an interval in which the sum resides using S sub 4. Okay, so let's start by finding S sub 4. Okay, so what that means is we're going to find the fourth partial sum. So S sub 4 is going to equal the sum of the first 4 terms of this series. So you can use a calculator for this. This is definitely a calculator sort of problem. And it works out to be approximately 0.8588. Okay? So we can say that S, which is the actual sum, the actual infinite series, we don't know what that value is, but we know it exists. We just found that it was finite. We can approximate that using S sub 4. Okay? We can approximate it better by using S sub 5 or S sub 6 or S sub 7, right? But S sub 4 is at least an approximation. Now the question becomes, how good is that approximation? In other words, how big is the error? Well, we call that error the remainder. So the difference between the actual value and the approximated value is going to be called the remainder. So depending on which partial sum we use, we're going to get a different remainder, right? The smaller the remainder, the better, right? So if we bump n up to something big like 100, then r sub 100 would be smaller, right? We'd be closer to the actual value. All right, so now there's a remainder theorem for these integrals that tells us that r sub 4 is going to be within an interval here. It's going to be smaller than the integral from 4 to infinity of f of x dx. But it's also going to be larger than the lower bound of the next sum. So this is n. This is going to be n plus 1. All right. Now, I'm not going to prove this, honestly, because I can't. But I do know that it has to do with the fact that RRAM is going to be an overestimate and LRAM is going to be an underestimate. So our actual value is going to be somewhere in between there. So that's kind of the flavor of why this is true. All right, so we can evaluate each one of these improper integrals. It's going to work pretty much the same way as finding the improper integral over here, except instead of using a 1 for our constant here, we're going to use a 4 or a 5. So instead of taking the arctan of 1, we're going to take the arctan of 4 or of 5. So that just means that this definite integral is going to be pi over 2 minus the arctan of 5. And this is going to be pi over 2 minus the arctan of 4. Now these particular values are not friendly unit circle values, but they are values that our calculator can deal with. And when you punch this into a calculator, you're going to find out that this is 0.1974 or so. And that's the smallest our remainder could possibly be. The largest our remainder could possibly be is this, which works out to be 0.2450. So that gives us a range for the remainder, right? So now what I'm going to do is I'm going to say, well, I know that the remainder is equal to the difference between the actual value and the fourth partial sum. Okay, so I'll go ahead and rewrite this real quick. And remember that we can add this this partial sum to everywhere. And also remember that we know what this fourth partial sum is. We found that earlier. It was 0.8588, according to our calculator. So if we add that particular value to our lower bound and to our upper bound, then we're going to get an interval within which our mystery value s resides. Okay, and that works out to be a lower bound of 1.0562. So s is at least as big as that, but is definitely no bigger than 1.1038. So using s sub 4, using our partial sum s sub 4, we can determine that s is actually somewhere between these two values. And these two values are actually fairly close to each other, so this seems to be a fairly decent approximation for our actual convergent value.